Hello, good morning. Welcome to lecture number 13 of CS 531 Memory Systems and Architecture. For this lecture, I have not prepared any slides because slides are not mandatory for this paper. This paper is very interesting, but I'll explain the concept directly from this paper. So, from today, we are starting a new concept, or you can say new technology, that is called cache partitioning. So what is cache partitioning? I think the basics of cache partitioning is already explained in class. There was a lecture I have uploaded where different basics of related to memory were discussed in short. So if cache partitioning concept is not clear, you can watch that my previous video. Here also I am explaining it very briefly again. So this diagram is, I think, this familiar to you. This is a multi-core architecture. So here I'm assuming only two cores. Each core has private L1 cache and both the cores sharing the last level cache. Okay, so cache partitioning means when multiple means different applications are running on different cores, so all the application will all share the resources of last level cache which is here L2. So this is also last level cache LLC. So cache partitioning means how to partition or how to divide the resources of the last level cache into different application or different cores. So here resources mean the allocation or space. For example, suppose there are two application 1 and application 2. Application 1 is running on core 1 and application 2 is running on core 2. So the one way is to is just give them uniform what you can say partition. So I'll give them like this. Suppose it means that 4-way to L1 and 4-way to 4-way to A1 and 4-way to A2. So both are giving equal importance here in this particular cache partitioning. But the thing is, every time it may not be true. Sometime what will happen, what may happen, that the behavior of A1 and behavior A2 are not similar. One may be very data intensive and another may be not data intensive, or it may be like this. One is cache friendly. I hope you know what is called cache friendly. Cache friendly means the application has high temporal locality. Another is maybe scanning behavior. So scanning behavior. So in that case, giving equal weightage is not at all a good idea. I think these the concepts are already discussed, because in replacement policy also the similar concept are discussed many times. But a common question that you may ask is, when we have discussed replacement policy, then also we have handled multiple applications, right? It's not like that when we discuss replacement policy, there was only one application and we are discussing it. It's not like this. We have discussed TADIP, we have discussed TADRRIP, then we have discussed ARIP. All these replacement policies were based on how to handle multiple application uniformly. So what is the difference between these techniques and cache partitioning? Well, the difference is not completely means there is a completely unique difference is not there. So there is a gray line. So sometime some cache partitioning techniques you can also consider as a replacement policy, or in some replacement policy you may also consider them as a part of cache partitioning also. So there is no special boundary between cache partitioning techniques and cache replacement techniques. But the paper that I am explaining here today, it is from 2006. So at that time this was a paper. So the concept that will explain the points that I have discussed here, these points are from 2006. It may be possible that all the points that they are explaining here, how they are trying to differentiate between replacement policy and cache partitioning, they are true in terms of 2006. In 2021 maybe some of this point is not correct, but that we will understand. But the point is, the paper that I will discuss today is a path breaking paper, not just for cache partitioning but also for replacement policies. Okay, so I'll come back to the paper later again. First, before studying this paper, some more basic about cache partitioning and the basics of cache, which will be required in this week, throughout this week, if we when we'll discuss cache partitioning. So the next thing that I will discuss here is the concept again, a concept of set associative cache again. So here each location, what we store in each location, here what we will store here, what are this? These are actually blocks, right? We store blocks here. So by means of blocks, what are the information we store here? If we say that, obviously we'll store data. This is one, this is the data block, right? Or you can say data block. That's the information that we fetch from main memory, that will be stored here first of all. But there are some additional bits also stored. One is called data bit, that need to be stored. Okay, data bit means if this block is a data or not. Okay, there are some other bits, a validity bit. Validity bit also is required here. Then if replacement policy is included here, then maybe replacement bits will be also there. Okay, so there may be many other then sharer state coherence information, many other things will be will be there. But all this thing, there is another information is called tag, which is very important. Tag is also stored. So basically we design a last level cache like any set associative cache like this. This is for your purpose. Actually any set associative cache is divided into two parts. It is actually divided into two parts like this, not just one. Here it is showing one, but instead of one, it's actually look like this. That should be two parts here. Okay, assume that this both are so this is actually data and this is actually tag. The tag is separate, so all this information, data bits, validity bit, everything stored here in tag. Actually there are some, if I maintain coherence, there will be some directory information and all those which are not relevant here, but all information are stored in tag directory. And there will be one-to-one mapping with this, has one-to-one mapping with this entry, one-to-one, this entry has one-to-one mapping with this entry, like this. So this is how a traditional set associative cache looks like. So whenever you want to search a block in the cache, you actually search the block in the tag array, and you are trying to match the incoming tag of the incoming address with the tag stored in that location. So this is the purpose of tag array. And once there is a hit here, you will go and collect the data from the corresponding location. This is a combined thing, and we call it as set associative cache. Why I am explaining this thing here? Because this concept of tag will be required here today, so understand cache partitioning. So okay, so the tag part is done. Now if I go back to cache partitioning again, so the cache partitioning that we will discuss today are called way-based cache partitioning. Way-based means we'll partition the ways, means we'll give 4 ways. If we go for this example that I said with this, then in this scenario 4 ways are given to A1 and 4 ways are given to A2. Right. So this it means that the partition will be applied to all the set uniformly. It's not like that here in this set it is 4 here in this set 5 3. It's not like this. If we go for this type of partition, it is very complicated. So in 2006 the idea they have proposed is to give a uniform partition. Uniform partition means 4 ways from each set to application and 4 ways to each set to application. That partition will be called as 4 suppose. Okay, it may be possible that sometime I'm giving 5 3. It means that 5 to A1 and 3 to A2. So this will be applied uniformly to all the sets. Now one more thing is, every time when I'll show it here, the partition here I'm showing that suppose I'm going for 5 3 or 4 4. Suppose if I'm going for 4 4, then what I'm showing here that the left 4 ways are for A1 and right 4 ways are for A2. Actually that is not true, but I'll use this example again and again. So this is a simplified version of cache partitioning examples. So I'll use it because it is easy to understand. But what you have to understand is 4 4 means, suppose you have this set and there are 8 ways. Suppose there are 8 ways, 1 2 3 4 5 6 7, there are 8 ways. Then if a partition 4 4 means that here there are 8 ways. So up to these 8 ways, there is 4 ways should be allocated to A1 and 4 ways should be allocated to A. It's not like they're contiguous 4 ways. It's not like this. For example, 5 5 3 means out of this 8, 5 should be allocated to A1 and 3 should be allocated to A2. So it's not like this A1, A2, A2, A1, A1, A1. That is also possible. A1 and last one is A2. That is also possible. If we go for that, they are also maintaining this partition 5, 3, 5, 3, because there are 5 A1, 1, 2, 3, 4, 5, and there are 2 A2. There are three blocks of A2. So this is how cache partitioning actually works. That the partition 5, 3 means, or for example, partition x comma y means x is allocated to a application and y number of ways should be allocated to another application, but it should not be contiguous. But here we are showing, we are giving a red line here and showing that this part is left part is for L1 and right part is left part is for A1 and right part is for A2. This is just for giving a simplified example. Otherwise, if we follow this idea, then the example will be very complicated. Okay, so with this basic concept of cache partitioning, let us start the first paper. The first paper is proposed is called utility based cache partitioning. We'll call this paper as, there is a, we'll use a short name of this paper, and short name will be UCP. This is the short name. Short name of this paper will be UCP. Utility based cache partitioning. Actually, this paper is published in 2006. I forgot the conference. Most probably it's published again in ISCA, but the document that I'm using today is actually a technical report. So why I'm using this, because this document is freely available, and if you just type utility based cache partitioning in Google, you can download this technical report. And this is the content of this is almost, I think, 99% similar with the paper they published to the utility based cache partitioning. So I'll call it UCP paper again, but for since I'm not using that paper, I'm using a technical report. There may be some minor difference from the paper, but I think most of the things will be okay. So this is the paper, utility based cache partitioning by Moinuddin Qureshi and Yell and Pat. So this is a paper, I think, from 2006, based on cache partitioning. This is the first paper, I think, on first and important paper on cache partitioning. So I think the basics of cache partitioning that I have explained in introduction section, I have already discussed with you. So one point here is, according to this paper, they have written that why a replacement policy is not enough when there are multiple applications are running. So you have to consider one interesting thing is, this paper is published in 2006. So, and whatever replacement policy we have discussed all started from 2007, right? DIP is from 2007. Then there were the thread-aware application, TADIP, then TADRRIP is from 2010, but the claim is from 2006. But the claim is it's not wrong. This claim is still correct. So, for example, if I go with this design, here, then in this design, the suppose there is no partitioning, nothing. One application A1 is running here and A2 is running here. There is no partitioning, and only there is a LRU replacement policy is here in this last level cache. So that LRU policy is not like that. It cannot handle both applications. It can handle every time. It will just remove the least recently one. That least recently used block can be either from A1 and A2. It will not consider that which from which application it is removing the blocks. It may be possible that it is removing blocks from one application every time. That is possible, that kind of starvation possible, but at least L1 can maintain this, right? So in this paper, that the paper that I'm explaining today, UCP paper, they have shown that if you maintain a LRU when there are multiple applications running on multiple core, and the replacement policy here in LLC you are maintaining LRU, then the partitioning is not optimal means the partitioning the cache will not partition according to the requirement of the application. That I will show you. If I go back to the paper, that I'll show you. But before this, I'll show you some example. If we see, there is example, I think this type of examples are familiar to you, because I have already shown this type of example when I have explained replacement policies, but it's almost similar. So if you can see here, what they have done in this paper, in this figure is, They have experimented two benchmark here, equake and VPR. There are two benchmark they executed. This is for MPKI. I hope you know what is called MPKI now, means per thousand instruction, and CPI. There are, this is for MPKI, this is for CPK as CPI, and this side, these are the number of ways. So what they did, they took a 1 MB 1 MB 16 way associative cache, 1 MB 16 way associative cache, and then they, what they did, they here means here 2 means the only, suppose this is your set associative cache, 16 ways are there. Suppose I'm not drawing all ways, there are 16 ways here. So initially 2 means there are only 2 ways are active, so these 2 ways are active, this part is off, this part is off. 4 means here only 4 are active, this part is off, like this. So this is this means what will be the MPKI if there is only 2 ways are active, what will be the MPKI if only 4 ways are available, what will be the MPKI if only 6 ways are available, when only 8 ways are available, and this means when all the ways, means the entire cache is available, and both the application run separately. So you can consider that it's, don't think that both application run in means parallelly on this processor. It's not like this. So first they have run this suppose VPR. So you can see VPR, once you have once you increase the size of the cache, size of the cache means basically when you are increasing the number of ways, you are increasing the size, right? So once the ways are increasing, then the MPKI is degrading. So better, lesser the MPKI, it's better, right? Miss. So if the miss is less, then it is better. So you can see the number of misses is degrading here. Slowly it is degrading. So and if we go for equake, then you can see how it is, initially it is degrading. If we are giving him 2 ways, then it is degrading, okay, but after 2 ways, if you provide more number of ways, it is not improving, it is still showing the same amount of MPKI. Why? Because this application is a scanning behavior. It has a scanning behavior, it is reducing, it is using some cache space, that is fine, but after that if you give more number of ways, it is not benefiting. So either it is a scanning behavior, or maybe the entire thing is fitting in the cache or something. So this type of application, so if you so now assume that both applications are running separately, sorry, both applications are running on parallel, in the diagram that I have shown like this, similar kind of. Now you can assume that application A1 is the scanning application, and application A2 is the cache friendly application of this paper. So in that case, they have shown that if we go for LRU policy, then the on average every time, means they have taken many examples, many times they have taken, and during this execution time they have taken examples. So on average the partition maintained is here. This is the LRU partition. LRU partition will be here like this. This is the partition maintained by LRU, means almost I think 9 ways are giving to this VPR, and remaining ways are giving to EQAC if we maintain LRU. Because if you are maintaining replacement policy, there is no means there is no direct partitioning plan, but since there is the LRU replacement policy, every time it will replace some blocks, right? So based on this replacement and all, they have checked many times that how many blocks from application 1 and how many blocks of application 2 are present. So based on this, they have checked that on average if we maintain LRU, then there will be 9 ways allocated to one application VPR, and the remaining ways to EQAC. But that is not the correct way, right? Because you can see from the figure that giving suppose if you are giving 9 to this, then maybe you are giving 7 ways to EQAC, but that is not correct, right? If you can see from this figure, giving more than 2 ways to this application EQAC is not at all a good choice, because if even you are giving him 7 ways, the performance will be same as giving him 2 ways. So the LRU policy is not enough. So that's why it is better to allocate ways to application based on its utility, how much it can utilize. If it is cannot, if here you can see the utility of equation is only 2, it can utilize only 2 ways. More than 2 ways, it is not utilizing it properly. So based on the utility of a application, the ways should be allocated. That is the main motivation of this paper. So what they will say, if you go for utility based, then maybe will give 13 ways, 13 or 15 ways to I think it is 13, so or 13 ways to VPR, and remaining 3 ways will give to equate if we go for utility. So now the question is how we'll measure the utility. So that is a question I am not asking, I am explaining now, but you have to understand that this paper is based on utility, means somehow they will measure the utility of these two applications, that how much utility is required for these two applications, and based on this utility requirement partition will be assigned. Okay, and this partition is not static. There are two types of partitioning that also I'm explaining here. So I think this is generic thing, so I'm explaining it here. There are two types of partitioning. One is called one is called static partitioning, and one is called dynamic partitioning. You have to understand, static partitioning means the partitioning is fixed, means during the boot time, when you will boot your computer, the partition will be fixed, and that partition will not change during the execution of the computer. Next time when you will shut down the computer PC and when you will restart again, maybe that partition will change, but during the execution of the computer, the partition will not change. That is called static partitioning. That we will not discuss in this course anymore, but you should know what is called static partitioning. Dynamic partitioning means it will change dynamically. For example, if we go for this here, it is, suppose it is 50 50 4, but after some time the behavior of application may change, or utility of the application may change. Maybe now the utility of A1 is very low, but after some time the utility of A1 may change. So in that case you have to change the partition dynamically. So that is called dynamic cache partitioning. So dynamic cache partitioning, UCP is one example is UCP that I am discussing now. It's a dynamic cache partitioning. So dynamically it will observe the utility, it will divide the cache, and now suppose at time t1 the cache is divided like 4, then it will, the last level cache will run it with this partition 4, but the utility monitoring system, there will be some utility recorder, right? So that utility recorder will again trying to record the utilities, and after some time, maybe at time t2, the utility will decide that okay, no, the partition 4 is not good anymore, so let us make it 5, 3. So in this way the partition may change dynamically based on the dynamic utilities of this application. So that is the behavior of dynamic partitioning. So these are the two division of partitioning that I am explaining. There are two more division that you have to know, what is called way-based partitioning and set-based partitioning. Set-based partitioning means number of set will be divided among multiple application, means maybe the, for example, if we go here, then maybe first two set will be given to A1 and next two set will be given to A2, like this. But set-based partitioning is very it is little complicated, because you have to change the mapping policy also, because otherwise the set index of application 1 is limited to first two set, and the set index of application 2 is now limited to the remaining two sets, so you have to change that. So this is little bit complicated, and again we are not discussing it in this class. So only thing that we'll discuss in this course is way-based cache partitioning, and which is very widely used also. Way-based means we are not all the sets will be allocated to all the application. The ways is divided, or that I've already explained, right? The 4 means uniformly applying 4 to all the sets. So here sets are not divided, so you don't need to do anything in set mapping and all. Only thing you have to just divide the number of ways. Only thing that you have to take care is this, that if your partitioning is 5, 3, then you have to take care that there should be a mechanism to take care that maximum 5 blocks of A1 should be there, and remaining ways should be allocated to A2. So this is how the concept of dynamic cache partitioning is. So I hope all these points are clear. So let us again go back to this paper. So this is their motivation, and that I have explained, that partition should be done based on utility. Then I'm not explaining all these things, but what I'm expecting from you, that you will read all this concept by yourself. Then I'll start with this section, motivational section. There are some graphs here, so let me explain all these things. So in this section they have shown some results. So there are 3 rows here. Each row has shown the behavior of some particular applications. So here you can see the first row, all the application. Here you can see if you are running this application on the system and you are giving number of more number of ways, then the you can see the application is not this is the I think which one, black one is mpk, so I will concentrate on mpk. So you can see this, the mpk is not improving much if we increase this. So for all the benchmark it is same here in this row. It is after some time it is not improving, or so it is here. If you go for here, then it is reducing up to here, but after 8 it is not improving. So here also it is after 8, after I think 4 it is not improving. If you allocate more number of ways to this application, it is not improving. So this type of the first one, the all this application that is shown in the first row, it's called low utility. Low utility means their utility is low. They cannot utilize the entire cache space, because you can, if you go, you can see here the if you give 4 ways to this application, here 4 ways to this application, then the mpki, and if you give them 12 ways or to this cache to this application, then the performance is almost similar. So it is not utilizing. So the utility of that this application here, this is low. So all this here, all these are low utility, utl suppose. So they are low utility based application. And if you go to the second row, you can see here, if you are increasing the number of ways, then it is also improving the performance, or also improving the mpk. Improving the mpk means reducing the mpk, right? All these application are similar behavior, right? If we go for this, this is I'm increasing the ways this side. So if you're increasing the ways, how I'm increasing the way, that I have already explained, right? Increasing the ways means I have a 16 way set associative cache, but I have forcefully powered off some of the ways. When I'm allocating 2 ways, then remaining 14 ways are forcefully powered off, like this. So if we increase the number of ways, then you can see here, sorry, increase the number of ways, then performance is improving. So it means that utility of these applications are very high. So these are called high utility application. These are called high utility, utl, high utility applications. These are high utility applications, and this is also I think mentioned here, high utility applications. So maybe I am not explaining this paper line by line, but it is your responsibility to read the paper line by line. It's a very interesting paper. And if we go to the third type of application, this third row, you can see that again here, if we give some rows, then it is improving, but after some time it is, after this it is not improving. Why? Because there is no option to improve. Because you can see that if we give 6 ways or 8 ways here to this application, then after that the mpk is almost 0. Here also it is all very less. And if you go here also, then if you give it for 6 ways, then after this the mpk is almost 0. So there is nothing to improve. So this type of applications are called saturating utility. Saturating utility means their utility is very limited. Even so, the entire block, if we give them 6 ways, for example here, if we go for this particular application, then if you allocate 8 ways, then entire application will be fit in the cache, and you no need to will not face any misses, or so there is no need of giving more ways. So these are called saturating utility. So it is mentioned here, saturating utility. So there are three kind of application basically. The one is called low utility, then it's called high utility, and another is called saturating utility. So if I try to relate it with the previous one, I think the application behavior that we have studied, like scanning and thrashing, I think the scanning and thrashing will have low utility, right? And maybe the thrashing one is also considered as high utility, because if we give more number of ways to a thrashing application, then maybe performance will improve. But I'll consider both scanning and thrashing here as low utility. You can relate it like this. So now the problem is, suppose you have, if I go back to my this example, where was my example, sorry, if I go to this diagram again, this the diagram in the circle. So if there are 2 application running, so now if a1 is low utility application and a2 is also low utility application, then I think it's not a problem. If a1 is a I think what I can say, it's a saturating utility, and a2 is also from saturating utility, then also I think it LRU can maintain it. We don't need to partition it in separately. But if the problem is, if any of this application a1 and a2, suppose a1 is a high utility application and A2 is a low utility application, in that case if, partitioning them based on utility is very much required. The same thing is, suppose if A1 is saturating utility, and A2 is low utility, in this case also you need to partition it uniformly, because if you give enough partition to A1, then you will not face any miss in A1 after some time. But if you are not partitioning it properly and giving more ways to A2, which is a very low utility application, and giving very less way to A1, and which makes this saturating application as high utility application. So we have to maintain this, that if the based on the application behavior we have to partition the cache. So, and that is, I think, written in this, that when why it is required to partition the cache. So this is the motivation of main motivation of this paper, that if there are different utility based applications are running on the computer, then the last level cache should be divided based on the utility. That's why this paper is called utility based cache partitioning, UCP. Utility based cache partitioning. So how this cache partitioning works, that is also very simple. I'll explain it with this diagram. If when you will read this paper, you will understand that the many of these concepts that are written in this paper you already know, because these concepts are related with the concept that we have discussed in replacement policies and all. So basically how it works, so this gray thing that you can see here, this is this gray part, UMON, partitioning algorithm, and UMON 2, these are the additional features, and remaining things are from the existing processor. So here there is a architecture, this is a core 1, this core 1 is private L1 cache, this is L1 cache, this you can say is L1 cache, this is core 2, and this is its L1 cache, and both the core is sharing a last level L2 cache like this. This is also you can say as LLC. So this diagram is same as the diagram that I am showing in the whiteboard, right? So the only thing is here they have not shown the LLC as set associative, but you assume that this is a set associative cache. This is a 16-way or 8-way set associative cache, this LLC. In fact, L1 are also set associative, but it is not relevant for us. So now how this partitioning algorithm works, so there will be two module here. It's called UMON module. UMON are actually called utility monitoring. I think the details of full form of UMON is written here. I think utility monitoring circuit is called UMON. So what is the purpose of UMON? And this is the partitioning algorithm. So purpose of UMON, see how see the placement of UMON. This circuit is placed between core 1 and LLC. This is called UMON 1, and UMON 2 is placed between the core 2 and LLC. So basically what this UMON 1 will do, UMON 1 will collect the utility of application 1 which is running here, core 1 suppose. So for simplicity, what I'll do, I'll assume that application 1 is running here and application 2 is running here. So what UMON 1 will do, UMON 1 will collect the utility of A1, and UMON 2 will collect the utility of A2, and both the utility will finally send to this partitioning algorithm, and then partitioning algorithm will partition the cache according to the utility received from UMON 1 and UMON 2, and that partition will be applied to this LLC. This is how they work, and this concept is repeating since it is a dynamic cache partitioning. So it's not like that the UMON 1 and UMON 2 will capture the behavior of application only once, and based on this they will partition, and there is no work for them. It's not like this. Once they partition the cache, again they will start the phase from the initial point, and again they will collect the utilities, and based on this after some time they may change it again. That was showing like T1 T2 in my in the whiteboard previously, right? Okay, so now the next question is how UMON is recording utility. So that is the most this is the main part here in this paper. So for this we'll see here that utility handling utility means they are checking that number of misses, number of hits you can allocate to this way. Suppose this is for this we'll just go for one particular set. I'm not showing multiple sets, but that in a set associative cache there are multiple sets, right? This but I'm explaining it to one set. So suppose how this utility monitor is actually saying that this is high utility, this is low utility. So what they will do, that when this core is running, right, so they will check that okay, if I give out, suppose there are how many ways, 1 2 3 4 5 6 7 8, there are 8 ways. So this utility monitor will check that instead of this A2A, if I give only two ways to this A1, assume the remaining are blocked now. So the what is how many, then what is the hit, if I give three ways to A1, what is the hit? If I give four ways to A1, what will be the hit? If I give A to all the ways to A1, what will be the hit? So this kind of hit it will calculate that, okay, if I'm giving A to A, then what will be the hit? If I'm instead of giving A to A, if I give only four ways, what should be the hit? So these hits will be counted. So basically they are doing the same thing that they have shown in the graph here, right? The graphs are also showing this is how the utility means here they are showing that if I am giving two ways, what is the performance of the application? If I am giving four ways, what is the performance of the application? So basically the same thing they are doing utilities. The utility means they are counting the number of hits. If I am giving two way, if I am giving eight way, if I am giving four way, all these things they're calculating by human. So now next is how they are calculating it. So let me explain this. So to calculate the utility, suppose this is the A2 associative LLC. So what the human one will do, human one and human two. So human one will what human one will do. So suppose I am concentrating on only one set, so it will check if all 16 ways. Sorry, that is not 16 ways. There are only 8 ways, right? In this case, so if all 8 ways are available, then what is the hit? If only 7 ways are available, then what is the hit? Then only 6 ways are available, then what are the hits? And like this, only if suppose only one way is available, then what are the hits? All these thing it will calculate. So there will be multiple values here. All this value it will calculate by, and these values will be sent to the partitioning algorithm. The same thing will do by human 2 also. human 2 also will calculate, and I'm saying it for only one set. So it may be possible that these records are required for all the sets, but this point I'm skipping now because I'll explain it later. So don't be confused, just assume that all these informations are sending for only one set, suppose. So here also for human 2 the similar kind of information will be sent, that for A to A, if A to A's are available for these, 7 ways are available for this, then what is the performance? So now the question is how human is calculating it. If 8 ways are allocated, then what should be the number of 8? If 7 ways are allocated, what should be the number of ways? How human is calculating? Because as I said, this is a dynamic partitioning and both the applications are running in parallel in this application. So the actual LLC is now using by both A1 and A2. So in that case, how you can simulate that if the complete 8 ways are allocated to A1, what should be the hit? If the complete 8 ways are allocated to A2, what should be the hit? How it is possible to calculate? Because this, it's not like this your cache is free. Cache is already running and cache is already data of A1 and A2. So for this it seems from here that you cannot use the cache storage or the actual cache to simulate this human behavior. To simulate this human behavior you need a separate text storage, and that is called ADT. I think, sorry, that is called ADT, additional sorry, ATD. I think it's not ADT, this is ATD. It's called additional text directory. That is they have discussed in this paper, but I am explaining it here again. So what they will do, as I said, each set associative cache has a tag part and data part. So this has tag and data part both. I am not discussing here this LLC. This LLC has a tag part, but this is individual for this LLC. Instead of this, they will use some additional tag array, and this additional tag array will be same tag array as this tag array. This will be just a copy of this. Suppose if this is a copy of this array, and what they will do every time, if you remember the position here, if I am going here, remember the position of human here, this is the position of human 1. So every time there is a request coming from core 1, when it is going to L2, it is also going to human 1, right? So in this way, what this human will do, ATD is a part of human. So every time there is a request going to this L2, this request is also coming here, and it will compare that, okay, what is the tag? They will compare the tag stored here with the newly coming tag. So now this entire tag, this entire concept that is maintaining here in tag array, the same thing will be maintained here also, and if there is a hit, they will count as hit. If there is a miss, they will count as a miss. So in this way, suppose here there are 16 ways available, the same copy. So this is, sorry, 8 ways. So this tag will work as this point. that if all the 8 ways are available, so the number of hit it is giving, suppose there is a counter here, that every time there is a hit, so this counter is incremented, so final value of this counter is you can put here. So now for the same then now you have to give for 7 ways also. So for example, you can use another no, let me use like a 4 way here when there are 4 ways. So maybe you can use another ATD when there is only 4 ways allocate, 4 ways is there. So this is a additional tag array. So now here every time so now what I am assuming here, this human has multiple ADT, this ADT is giving you the result for 8 way when 8 ways are on, this ADT is giving you result only 4 ways are on. So maybe there will be another ADT here that is where there is only 2 ways are on. So in this way you need multiple additional tag arrays, one tag array for each one, each utility, 8 way, 7 way, 6 way, 4 way, and there will be a counter here. So based on this counter value, this counter value will be supplied to the partitioning algorithm, and based on this partitioning algorithm will decide what should be the utility. Because if suppose the value of 8 here is suppose here it is 40, here it is 40, 6 way it is suppose 50, like this. So based on this value it can calculate that okay, which where is the saturating point, where is the saturating utility, means after this if give more utility it is. So based on this value you can actually calculate whether this application is a low utility, high utility, or saturating utility, right? Okay, so if all this thing is clear, then again I'll go back to the paper. Then so basically what I have explained till now is how emmons are actually implemented. But so this is the complete section of about emmon. So it is written here: monitoring the utility information of an application requires a mechanism that tracks the number of misses of all the possible number of ways. So I said it in terms of hit, and they are saying it in terms of miss. It is similar, right? If either you are counting hit or you are counting miss, it's almost similar thing. So they are saying the tracking the number of misses here. But the problem here is the concept that I have explained, that is technically theoretically correct, that for each utility you will use separate ATD, additional tag directory. But the concept is the hardware overhead will be very very high, because I have explained it for only one set, there are multiple sets like this, right? So the hardware overhead will be very very high. So there should be some alternative way, because see the tag directory you are copying you are, and you are not just copying it for only once, you are for utility human one only you are copying it many times, and for human 2 also you have to copy it. So that solution is theoretically correct, but in real situation this is not correct. So in real scenario you have to go for some other techniques. So the other techniques they use is, instead of going for multiple ADT, we can only go for one ADT of the bigger ADT. Or if I go back here, they're saying no, you no need to use all these ADT, these ADTs are not required, only this ADT will be enough, this ADT will be enough. The how the but this has all 16 ways on, so how this will be enough to calculate, sorry 16, not 16, this is 8. Actually the paper is showing 16, and I am using a diagram here for 8, that's why it is confusing. So but I hope you are understanding it. So here it is 8 ways. So how only one ADT having 8 ways enough to calculate that, if what will be the utility when there is 2 ways available, 3 ways available, 4 ways available, that we will check now. And that is the property of last level cache, and that property that are explaining. So suppose there is one set, and for this set there are multiple counters like this counter is for MRU position, this is and this counter is for LRU position, and these are the remaining counter for remaining 2 position, hit counters. Okay, so now what they are saying that suppose this kind of tag array is maintained by umon. So now every time there is a hit in this MRU position, this counter will be incremented. There will be hit in this position, this counter will be incremented. If there is a hit in the LRU position, then this counter 3 will be incremented. So based on this, suppose this is the result. After some time they found this is the result means you can see there are 30 hit in MRU position, 10 hit in LRU position, and 20 hits in the next of MRU position, and the 15 hits is just the previous of LRU position. So there are out of 100 there are 75 hits are there, and total misses here that's in 25. Okay, so now the important property here, if it is a LRU based replacement policy, then it is fine. It has been found that if your number of misses, if there is a hit in MRU, suppose if there is a hit here in position 1, then this position, let me check. The property is, if suppose in the, if there is a hit in this position, so now if we allocate if two ways, then also there will be here hit in this position. If you allocate three ways, then also this will be hit. This is written here that if containing n ways is guaranteed to also hit if there is more than n ways. So suppose if now there are n ways is allocated to an application, and now there is a hit in this position, n is more than 2 suppose. So and that hit is also guaranteed if you give them more number of ways, means in place of n, if you give him n plus 10 ways, then also at position 2 there will be hit. And that is also showing here. So if you see the graph, you can say number of ways per set. So now if here in this application, if we remove one, instead of 4 way, if you remove this way, means assume that only 3 ways are available, then the number of hits will be 65. This 10 will become miss, this 10 will become miss. If we give only 2 ways, then remaining this 10 and 15, this 25 will become miss. So only 50 will miss, 50% will be hit and 50% will be miss. If we give only 1 ways, then only 30 will be the hit, remaining thing will be misses. So it means that if we maintain this type of counter, then only one edit is enough to show you utility of 8 way, sorry, all the ways. Means here in this case 1 way, 2 way, 3 way and 4 way, all the utilities you can find out if you maintain the counters like this, and this has been explained here. So it means that instead of multiple ADT, you can go for one ADT, and for each set and for each location you have to go for a counter like this. I hope this part is clear. But again, this is not a good, still the hardware overhead is more. Why? And that is shown here. If we go next, I think there is a diagram here. So the concept that I have just explained, if we go for that concept, then each ADT should look like this. Sorry, every time I'm saying ADT, I think it is ATD, additional tag directory, I think ATD. So each tag ATD should look like this, the way I have explained here. So where they have explained in previous diagram, that suppose this is ADT, for there will be multiple tag set here. So for each set there will be multiple counters, one counter for each LRU position, MRU position, LRU position. So that should be there. So this is called, this design is called UMON local. They have shown multiple design. So here in this design also the hardware overhead is more, because for though UMON 1 has only one ATD and UMON 2 has only one ADT, but if we go inside to that ADT, there are still you need to maintain multiple sets, and for all this set, this is you are storing tag, because this is a additional tag array, right? And for each you are also maintaining a counter for each position. See how many counters are there. So this is very, very harder, till the harder overhead is more. So what they said here, they said that no, instead of going for this, maybe we can go for UMON global. UMON global means no, we will not maintain counter separately for each set, will maintain counter common counter for all this set. That's why this design came. And the moment you come for this design, that means the main concept of wave partitioning coming from this design, this design. Why? Because main concept of wave partitioning said divide the ways uniformly in all the sets. If you go for this design, if somehow it is possible to go for this design, then maybe you can choose a best partition for each set separately. Maybe here in this set you can say no, it is 5 3. Maybe in this set you can say no, it should be 3 5. You can go for individual partition if for each set, if you are going for this this diagram. But that is not theoretically possible, technically possible, because of the hardware overhead. So it's better to go for human global. Human global says there are in ATD. So remember what I am saying, discussing everything here, it is because of auxiliary tag array. Sorry, not additional tag array, it's auxiliary tag array. Don't consider this, all these thing that that showing in this figure are LLC. These are additional thing. This tag array is additional tag array. Okay, so the in global there are multiple set, all the set are to using one common counters, right? So this is called human global. So these counter values will show you the common utility, global utility, and when you partition it, you can only partition. For example, if you are partitioning it 5,3, then 5,3 is applicable to all the set uniformly, right? But again, if we go for this has also many significant hardware overhead. Because of why? Because here the number of counters are less, but the important part is you are still copying the tag array, right? if you go for my diagram here, this is the ATD, right here. This is the ATD. So if you see number of tag entries here and number of tag entries in actual LLC are same. So you are still copying the complete tag array here, and you are copying it twice. If there are two codes, this is for human 1, there will be same thing will be there for human 2. And if there are multiple codes, then every time you are copying the tag array of LLC for maintaining one human. That is also not at all a very practical solution. So what is the even better solution? So for going for even better solution, they will go for this term, dynamic set sampling, DSS. I hope you already know what is called dynamic set sampling, right? Dynamic set sampling means instead of going for all the sets here, there are multiple sets here, and instead of going for all the set, they will go for some selective set, and they will apply this they record the utility based on those selective sets, right? And then that will be applied to the remaining set. I am not explaining DSS in more detail because you know it, but the interesting point is this paper is from 2006, and the concept of DSS, that you know that those papers are from 2007, right? So it means that the DSS concept that you discuss, that you find that DIP paper is using, these actually first introduced in DSS here in this paper. Actually this is not introduced in this paper, this is a separate paper, but the authors are same. And you can see the concept of DSS. I think there will be a see, dynamic set sampling is proposed in reference 14 here, but I think this, as far I remember, this is the same authors who have proposed dynamic set sampling. And first of all, they use dynamic set sampling here in UCP, utility based monitoring, and then other authors, I think other papers like DIP paper and other paper also started using DSS. Even today people use. So last week I have explained Hawkeye. It's a replacement policy proposed in 2016. Even 2016, and even after that also people are using DSS. Okay, so this is the best human. So if I go for a simplified one, let me go again to the diagram, that this is the main diagram of cache partitioning. So here there are two human required, human 1, human 2, because there are two cores. If the core is more, each core basically need a individual human. But now the human circuit is very hardware overhead is very reduced. We will only go for some limited sets. So if there are multiple set in last level cache, we will not go for all the set. We will just maintain the tag of limited set here in human, and from all these tags we are not maintaining counter individually for each set. We will maintain counter only global counters, and so and will collect the global utility of all the sets, basically not all the set, the limited set of DSS, and based on this utility information will partition the last level cache. So now the purpose of utility monitor and how the utility monitor or human is implemented, this thing I think it is clear. DSS part is explained here, you have to read this. Okay, and now this part here they have shown that how dynamic set sampling is perfect, means how instead of going for many set, if we go for limited number of set, how it is giving proper results, that they have explained it mathematically here. I'm skipping this part, you read it. And then at the end of this they said that they have, instead of using many sets, they use only 32 sets for utility monitoring, or sorry, for DSS. Now the main question is, suppose partitioning information, partitioning algorithm, that is the in the middle module, that module now knows the utility of from all the utility values from human 1, all the utility values from human 2, then how this partitioning algorithm is partitioning the cache. So for this they use this algorithm. So let me explain this algorithm with some example. If I go here, let me minimize it first. Okay, I need this diagram also as well as here. So if I try to explain it, so basically this is they are calculating a formula called U total. So what is U total here? First of all, you will go for we'll go for UA1 Z1. Sorry, I'll remove A1. This I'll only go for UA1, and this is UB. If there is 1, then there will be 15. It means that if application A is giving only one way and application B is giving 15 ways, then what should be the value? So this is one value. So same value will be given like if A is giving 2 ways and UB is giving remaining ways and 14 ways, then UA is 3 ways plus UB is giving 13 ways. Like this, UA is giving 15 ways plus UB has given means application B has given only 1 way. Then what will be the value? So I think all these values is possible to collect from the information that is providing by the utility monitor. Are you agreeing with me or not? Because what I am saying, the information that is collecting from utility monitor, from that we can say that if only one way is giving to the application, what will be the hit? If only 15 ways is 15 ways is giving to B, what will be the hit? If we go for this case, this row here, it is saying that this row needs that what will be the hit if only 3 ways are giving to A and if 13 ways are giving to B. So all this information can you collect from the information that is sending by human? Yes, it is possible. If it is not clear to you, again go back to the exam entire paper, read it, revise my lecture. You will understand that how the information sending by human, which is enough to collect all the information. So now from all the information there will be values here. Each row will give a value. So now the maximum value will be collected as U total. So suppose assume that maximum value is giving by this row. If maximum value is giving by this row, then partition should be 3 comma 13. Sorry, partition should be 3 comma 13 because of this 3 and this 13. If maximum value is giving by this one, then the partition should be 2 comma 4. So in this way, this final partitioning information will be sent and the last level cache will be partitioned accordingly. So this is the algorithm. This is the based on this algorithm, this partitioning is happening. Now only one thing is that point is written is changes in replacement policy, that I'll explain in a whiteboard. But after this, I think this paper is concept is done. Now experimental concept section is started from here. So you have to understand till this point of this paper. This paper is very important for, and all the cache partitioning techniques. For all the cache partitioning technique, this paper is the baseline paper. So I'm explaining it in more detail. I'll not explain other paper in this detail, but this paper is very important because this is the baseline of most of the cache partitioning. So this is their partitioning algorithm. And again, if I go back to their diagram, main diagram, I think diagram will be more clear now to you. This is their main diagram. Now E1 is collecting information, E1 2 is collecting also collecting utility information. These two information are sending to partitioning algorithm, and partitioning algorithm is doing these calculations, and based on this it is finding out the best algorithm, best partitioning, and this partitioning will be sent to last level cache, and last level cache is partitioning as per the recommendation. But the question is only one thing is that why they say the replacement policy need to be modified. Suppose this is the current partition, this is the application, and suppose this is your current partition, this is the current part, this part is A1 and this part is A2. After some time, if it is recommending that no, partition should be changed from here to here, partition should be changed from here to here, so these ways are now need to be allocated to A2, right? But currently they are allocated to A1. After partition change, partition will come from here to here, so this block should be allocated to A2. So how this block should be allocated to A2? So one thing is, when the partition is changing, just simply remove these blocks, right, when the partition is changing. But that is not the correct way, because otherwise this, if we, when partition is changing, if we remove all the blocks of A1 from here, then it may degrade performance. So what you have to do is let the replacement policy handle it. You will not, when partition change, simply partition will change from here to here, and nothing will all this thing will not happen. Okay, partition is changing, so what it will do, partition, this is the cache, this was the initial partition. Now partition will change to here, this is the new partition, and this is the new partition. So now what will happen next time when you want to replace something, then replacement policy will take care of this, that instead of replacing the block from A2, it will give more preference to replace a block from A1, such that the new partition can be validated after some time. So now if the partition is 5 3 and after and the new partition is 3 5, then what the replacement policy will do, replacement policy will every time, for if it is partition to if it is now already moved to new partition, then what the replacement policy will do, when it will select a victim block, maybe every time it will not select the LRU as the victim block, it will select a victim block from A1 only, such that the partition of A1 can be reduced and the partition of A2 can be increased, and after some time the situation of this will be converted to this. So this is how there will be slow transition is required, and this slow transition will be maintained by the replacement multiplication policy. So I hope it is clear. So I am advising you to read the complete paper. It's a very interesting paper, you'll understand it. If anything is not clear, let me know. And from this week I'll explain 2-3 more partitioning techniques, but all these will be based on UCP, so I'll quickly explain all these things. I'm stopping this lecture here. Thank you for watching.